More earthquakes in the New Madrid Fault. What's going on? Most people in the United States and perhaps around the world only know one fault line by name, the San Andreas Fault, which runs almost the entire length of California and is often said to be on the verge of triggering the big one. However, for at least the past 20 years, geologists have been telling us something different. That the real danger for the USA on a much higher level comes from a seismic region that the media, busy emphasizing the threat that inevitably destroys Los Angeles in disaster movies, have paid very little attention to. Yes, we're talking about the New Madrid Seismic Zone, which has recently been shaken by a series of earthquakes. Weak, but absolutely unsettling. In this video, we'll try to shed some light on this and answer an intriguing question that arises from examining the chronology of earthquakes in this area. Namely, do earthquakes have a preferred season to occur? And do those in New Madrid perhaps favor the winter? One thing is almost certain. When thinking about earthquake risks, the hills of western Tennessee are not the first thing that comes to mind. But as we are about to see, it would be a mistake to underestimate them from this perspective. Just east of the famous subduction zones of California and the Pacific Northwest lies the New Madrid Seismic Zone. This highly active area includes parts of Tennessee, Kentucky, Indiana, Missouri, Illinois, Arkansas, and Mississippi, and is responsible for the largest historical earthquakes in the United States east of the Rocky Mountains. Experts warn that a major earthquake near the town of New Madrid today would cause extensive damage to buildings, bridge collapses, disruptions to essential services, and failures of levees and slopes for hundreds of miles. It's a threat that those living and working in the region cannot afford to ignore. But why such pessimism? The answer, at least for now, lies not in the present, but in the past. We know for certain that in December of 1811, an invisible force gripped the central Mississippi Valley and did not let go for weeks. A series of major earthquakes caused the riverbed to rise and fall as if it were a stormy sea. On February 7, 1812, just upstream from New Madrid, the land was deformed to the point that the mighty Mississippi began to float north instead of south. That event was the culmination of a period of terror known as the New Madrid earthquakes. This period began exactly on December 16, 1811, when at 2 in the morning, the first shock hit what is now the southern tip of the state of Missouri. Residents of both rural and urban areas woke up to furniture bouncing and porcelain dishes shattering. Then the houses literally began to move off their foundations. Anyone who could rushed into the streets and stayed there, trembling from the cold and fear. For many others caught in their sleep, the once peaceful and safe homes suddenly became deadly traps. In the hours before dawn, the ground continued to shake, though with less intensity. Around 7 o'clock, there was another violent shock. Then, around 11, there was an even stronger one. Fissures opened in the ground, spewing mud and sulfurous gas that contaminated the air. Eyewitnesses saw thousands of birds flying away from the area as if they had gone mad. When the violence of the tremor ceased, Little Prairie, a town in Missouri, was completely leveled. Lesser tremors continued until January 1812, and on the morning of January 23rd, around 9 o'clock, another strong earthquake struck the surviving population. Point Pleasant, already battered, was near the epicenter, and the inhabitants fled. When some returned in February, they realized that the town was gone. It had all slipped into the Mississippi. But it wasn't over yet. The disaster continued to strike the region. On February 7, 1812, before dawn, the restless sleep of the inhabitants of that area was again interrupted by tremendous seismic waves. The epicenter was beneath them. This earthquake, more violent than all the previous ones, was so strong that in Cincinnati, Ohio, 650 kilometers away, it knocked down chimneys. The fury of the earthquake, however, was particularly unleashed on the river town of New Madrid. The shocks of 1811 had already severely damaged the small town, killing several residents and forcing most of the survivors to leave. But the quake on February 7th delivered the final blow. The tremor was so powerful that within 3 minutes, seismic waves reached Charleston, Washington, and Boston. The shaking lasted 15 minutes, and needless to say, even the sturdiest brick and stone houses collapsed to their foundations for miles around. St. Louis and Louisville suffered significant damage. Aftershocks pounded the region for days. Out of a population of about 15,000 in the affected area, the death toll exceeded 1,000, and at least 5,000 people were left homeless. You might think that the human losses weren't as terrible compared to the recent carnage in Haiti in 2010 and Turkey in 2023. But you'll change your mind when you consider that at that time, the population density was 1 person per square kilometer. We also have to account for the deaths among the native populations, whose numbers were never known. In their territories, too, the ground was ripped apart and then covered with sand boils, fissures, and crevices. Dead trees were everywhere. Swamps were lifted and drained, while good pasture land was submerged by new enormous lakes, and countless Indian villages vanished from the face of the earth. The still young United States had never experienced a disaster of such magnitude. It's impossible to determine the exact magnitude of these earthquakes, as seismographs didn't exist in 1812. But it's believed that the most violent one far exceeded magnitude 8, making it one of the most intense ever observed in the continental United States. And this is just a quick account of what happened more than 2 centuries ago. A catastrophe that, thanks to the very low population density of the affected areas and the slow speed at which news spread back then, was soon forgotten by everyone, even the central government, which didn't even bother to bring aid to the survivors. But all this concerns the past. If we want to deal with the present, we must get used to the idea that seismic activity in this area still exists, and that in the meantime, the overall population of those places has risen to 5 million people. It would be an apocalypse if the shocks of 1811-1812 were to repeat today, don't you think? And it's easy to understand why with a simple calculation. If 2 centuries ago the percentage of victims relative to the population was 7%, not counting the losses among the natives, which are hard to compute, with a quake of the same power today, we should expect at least 300,000 deaths. A massacre. Okay, but so far we've only talked about the effects due to the region's seismicity. But what about the real cause? That is, what kind of monster lurks in the depths of these seemingly peaceful hills of Missouri? It was only in the early 20th century that the area began to attract numerous scientific expeditions, with flocks of geologists eager to understand what could have caused such intense earthquakes in a region where there are no surface faults like California's San Andreas. After decades of digging and studying, it was understood that the seismic activity in New Madrid is not due to the tug-of-war between 2 opposing tectonic plates, as is usually the case with most violent earthquakes. The critical zone is not on the edge of a plate, but near the center of the North American plate, buried 600 to 900 meters deep under thick river sediments. It's not surprising that even areas far from plate boundaries are occasionally hit by earthquakes. Even the largest and most stable plates, where geological movements ended billions of years ago, can sometimes experience internal deformation, mainly due to the pressures exerted on their edges. Another theoretical reason for the development of intraplate earthquakes could be the birth of a new margin, that is, a new rift zone caused by the splitting of a plate into 2 distinct plates. This seems to be the most likely case for New Madrid. It's estimated that 0.5% of the seismic energy released worldwide is attributable to earthquakes that originate far from plate boundaries. The remaining 99.5% is due to the more numerous and stronger ones that occur along plate margins. In the case of New Madrid, the harder, colder, drier, and less fractured crust of central United States can generate shocks over larger areas compared to earthquakes of comparable magnitude in the west. The geological structure of the New Madrid Fault Zone consists of layers of sedimentary rock like limestone, which spreads and amplifies the shocks, much like hitting a bass drum. Because of this chain effect, an earthquake along the New Madrid Fault Zone would travel farther and cause more damage than an earthquake of similar magnitude on the west coast. Today, the New Madrid Fault Zone, which is active, continues to move, holds the highest seismic risk in North America east of the Rocky Mountains. As we've already mentioned, earthquakes cannot be predicted, but probabilities can be calculated based on evidence of past seismic activity. Scientists estimate that in New Madrid, there is a 10% chance of an earthquake with a magnitude greater than 7.5 on the Richter scale occurring in the next 50 years, and a 25 to 40% chance of a 6th or 7th magnitude earthquake in the same period. All of this, of course, would result in significant damage and loss of life. Currently near New Madrid, an average of 200 earthquakes occur each year, most of which are too small to be felt. About once a year, a magnitude 3.0 earthquake occurs, and about once every 10 years, a magnitude 5.0 or higher earthquake occurs. Hey guys, just a moment before we continue. Be sure to join the Insane Curiosity channel. Click on the bell, you'll help us to make products of even higher quality. But is the New Madrid Fault still active and continue to pose a high risk to the population? There is no doubt about it. The tremors, those below magnitude 2, are imperceptible to the population but are still recorded by seismographs, occurring daily. And very frequently, at least once a month, there are those above magnitude 3. And just recently, we had proof of this, specifically on December 9th, when, within a few hours, a seismic swarm originating at a depth of 9 kilometers affected the area. According to Missouri's State Emergency Management Agency, 5 earthquakes were detected near Marston, Missouri, while 2 were detected near Ridgely, Tennessee. The strongest shock reached a magnitude of 3.0, and not all residents felt it. It's not much, but this trickle of vibrations still prompts us to never let our guard down. At Insane Curiosity, we use these insights to keep telling stories, doing our best to inform and warn, and also to spark some curiosity. For example, have you ever wondered if earthquakes have particular months or seasons when they strike with greater intensity? Personally, I asked myself this question while researching for this video, as I came across certain coincidences that I then tried to understand better. What coincidences? Well, mainly the fact that all the largest earthquakes in the New Madrid Seismic Zone have practically occurred during the cold season. Obviously, all those from 1811-1812, but not only those. In the list of earthquakes that have exceeded magnitude 4 since then, more than 70% occurred in the colder months, from October to March. This includes the strongest earthquake in this region since 1900, which occurred on November 4, 1903, with a magnitude of 5.1. Just a coincidence? Probably. But after reading various documents on what I'm about to summarize, I was convinced to find an alternative explanation, which I'll give you right at the end of the video, just before we say goodbye. There are many myths about earthquakes. One of the most widespread is that there is something called earthquake weather, which refers to weather conditions that usually precede earthquakes, such as hot and dry or dry and cloudy. The myth comes from the Greek philosopher Aristotle, who in the 4th century BC hypothesized that earthquakes were caused by very hot winds escaping from underground caves. With the advent of seismology, the science that seeks to rationally explain these phenomena, we now know that most earthquakes are caused by tectonic processes. That is, forces within the solid Earth that cause changes in the structure of the Earth's crust, mainly the breaking of underground rock masses along fault lines, linear zones of weakness. We also know that most earthquakes occur well below the Earth's surface, far beyond the influence of surface temperatures and conditions. Finally, we know that the statistical distribution of earthquakes is approximately equal in all types of weather conditions. Myth busted then? In fact, according to the U.S. Geological Survey, The only correlation that has been noted between earthquakes and weather conditions is that large changes in atmospheric pressure caused by major storms like hurricanes have occasionally been shown to trigger what are known as slow earthquakes, which release energy over relatively long periods and do not cause ground shaking like traditional earthquakes. The same scientists also assert that while such large low-pressure changes could potentially contribute to triggering a damaging earthquake, the numbers are small and not statistically significant. That's for the weather. But what about the climate? Could there be connections between recurring seasons and earthquakes? To answer this, we must first determine what types of tectonic processes could be related to climatic phenomena. Scientists know that earthquakes can be triggered or inhibited by changes in the amount of stress on a fault. The largest climatic variable that could alter fault stress loads is surface water in the form of rain and snow. It seems that several studies have already supported such connections, but there's a problem. Generally, we've seen this type of relationship in microseismicity, small earthquakes with magnitudes less than 0, much smaller than what humans can perceive. In this regard, it seems a link has been found between the amount of microseismicity in the Himalayas and the annual monsoon season. During the summer months, large amounts of rainfall fall on the Ganges Plain, which includes the northern regions of the Indian subcontinent. This increases stress loads on the Earth's crust and decreases levels of microseismicity in the adjacent Himalayas. So during the dry winter season, when there is less water weight in the crust in the plain, the Himalayan microseismicity peaks. This is also confirmed by a recent study published in Science Advances, where researchers report that episodes of heavy snowfall and rain have likely contributed to a swarm of earthquakes in recent years in northern Japan. The study is the first to show that climatic conditions could give rise to some earthquakes, focusing on a series of ongoing earthquakes in the Noto Peninsula in Japan. The team found that seismic activity in the region is surprisingly synchronized with certain changes in underground pressure, and that these changes are influenced by seasonal patterns of snowfall and precipitation. In short, the research shows that snowfall and other surface environmental loads impact the stress state underground, and therefore the climate obviously impacts the response of solid Earth, and part of that response is earthquakes. Scientists suspect that this new connection between earthquakes and climate might not be exclusive to Japan and could play a role in affecting other parts of the world. But they also say it's much more difficult to draw similar conclusions for larger earthquakes. The point is that we still don't know when a fault might be at the critical point where pressure related to a climatic process could be the straw that breaks the camel's back, causing a significant earthquake. And what about drought? We know that seasonal effects can cause changes on faults, but what about less periodic climatic phenomena like a long-term drought? Could they also cause changes? It appears that changes in stress loads on the Earth's crust due to periods of drought can indeed be significant. Research conducted by JPL scientists in 2017 found that alternating periods of drought and heavy precipitation in the Sierra Nevada between 2011 and 2017 actually caused the mountain range to rise by nearly an inch and then fall by half an inch. This happened because the mountain rocks lost water during the drought and then regained it. The study did not specifically examine the potential impacts on faults, but such stress changes could potentially be felt on faults in or near the range. Similarly, it has been shown that groundwater pumping from underground aquifers, which is often done recklessly during drought periods, impacts stress load patterns by unloading the Earth's crust. A 2014 study published in Nature examined the effects of groundwater extraction in California's Central Valley on the seismicity of the nearby San Andreas Fault. Researchers found that such extractions can increase stress levels on both sides of the fault, potentially causing the tectonic plates to slip and release seismic energy. These stresses are small, but if groundwater pumping continues over a long period, they could become more significant, potentially accelerating the onset of the next big earthquake in the Los Angeles area. Another climatic phenomenon believed to be connected to tectonic processes is glaciation. The retreat of a glacier can reduce stress loads on the underlying Earth's crust, affecting the movement of subsurface magma. A recent study in the journal Geology on volcanic activity in Iceland between 4,500 and 5,500 years ago, when the Earth was much colder than today, found a link between deglaciation and increased volcanic activity. Conversely, when the glacial cover increased, eruptions decreased. It has also been shown that the rapid movement of glaciers can cause so-called glacial earthquakes. Glacial earthquakes are intense seismic shocks, with magnitudes greater than 5.1, occurring in areas where the glacier moves faster than 1 kilometer per year. The number of glacial earthquakes in Greenland peaks every year in July, August, and September, and the number is increasing over time. This increase seems to be related to the progression of global warming. Moreover, many scholars believe that poor water management and usage by humans can influence earthquakes through a phenomenon known as induced seismicity. For example, in 1975, about 8 years after the formation of Lake Oroville in Northern California, the state's second-largest artificial reservoir, a series of earthquakes occurred nearby, the strongest of which registered a magnitude of 5.7. This happened shortly after the water in the reservoir was brought to its lowest level to repair the dam's power plant intakes and then refilled. Several studies investigating the reasons for the seismic event concluded that fluctuations in the reservoir's water level and corresponding changes in the water mass's weight had altered stress loads on a local fault, triggering the earthquakes. Monitoring seismic activity in the reservoir in the years following the earthquakes established a seasonal correlation between the reservoir's water level and seismicity. Seismicity decreases as the reservoir fills in winter and spring, and larger earthquakes tend to occur when the reservoir level drops in summer and fall. So what can we conclude from everything we've discussed so far? We can say this. Until recently, the study of seismic activity was entirely focused on understanding plate tectonics and the processes occurring within the Earth's crust. But now things are changing. In the last decade or so, with the widespread adoption of new technologies like GPS, which have greater spatial distribution and sensitivity, seismologists have started looking at other factors that might influence earthquakes, such as climate, the role of water and ice masses, and seasonal differences. The challenge, however, is to align these connections with fundamental physics. We're certainly not close to predicting when an earthquake might occur due to climatic processes. Even if we know that an external climatic process is potentially influencing a fault system, we still cannot understand if that fault is on the verge of breaking, and if the climate will be able to give it an extra push to make it rupture. The picture is still quite hazy, but at least we can say that understanding that climatic factors can also have an impact gives us an additional element of judgment. Well, after all these considerations, which largely seem to support a small role of climate or environment in triggering earthquakes, why not think that the enormous and variable pressure exerted by the great mass of the Mississippi River can influence the seasonality of earthquakes in the area where the fault and the river intersect in the New Madrid region? The flow of the Mississippi is characterized by wide variations depending on the location and season, generally ranging from 8,000 cubic meters per second to 50,000 cubic meters per second. And during floods, the flow can easily rise to 70,000 cubic meters per second, with a record of 300,000 cubic meters per second measured during the 1928 flood. Could it be? What do you think? If this has been confirmed for changes in the level of the artificial Lake Oroville, why not think that the enormous difference in the flow of the Great River could lead to the same consequences? In any case, the small town of New Madrid, now taken as a symbol of earthquake risk in the region, reportedly tends to take it philosophically, content, as some say, to keep one eye on the Mississippi and one on the hills. New Madrid folk singer Lou Hobbs puts it another way in his signature song, Living on the New Madrid Fault Line. The good Lord, He puts us all here, and only He's going to take us away. Living on the New Madrid fault line, you gotta live it day by day.